Right, welcome. So now we're going to learn to take the derivative of logs other than just base e. All right, so the derivative of log base a of x is going to be 1 over natural log of a times x. So very much like when we took the derivative, when we had, we changed from e, taking the derivative of e to the x, to taking the derivative of some other base raised to a power. Right, we had to multiply by natural log of the base. Well, now we're going to do the same thing, but we're going to be dividing by natural log, right? Because those are, you kind of think of it as exponential log or inverse operations there. If we have something other than just an x, then it's going to be the derivative of whatever we're taking the log of over natural log of a times f of x. So a little review here, our exponential derivatives, if we have f of x equals e to the f of x, that would be, the derivative would be f prime of x equals e to the f of x, exact copy, times the derivative of the exponent, times f prime of x. If we have something other than e, we're going to have the exact same thing, f of x equals a to the f of x power, f prime of x equals the exact copy, a to the f of x, times the derivative of the denominator, but one other little part, times the natural log of the base. For the derivative of natural log of f of x, right, the derivative, f prime of x, is going to be 1 over f of x, 1 over whatever we're taking the log of, but times the derivative of that value. So that would be f prime of x divided by f of x. And if it's not base e, but some other base, we're going to do the exact same thing, except we're also going to be dividing by the natural log of the base. Right? So just reviewing all of your exponential and log derivatives. So let's try this one. All right, so as a reminder, the derivative of log base a of f of x is equal to f prime of x divided by f of x times natural log of a. All right, well now these ones though, there's just an x. All right, so it's just going to be 1 over x, but then also divided by the natural log of the base. So this one's a pretty easy one. G prime of x equals, right, so the derivative of x is just 1, so this is going to be 1 over x natural log of the base, which is 2, minus scalar multiple. If you're taking the log of something times a scalar multiple, it's just that same derivative. If we're taking the derivative of something times a scalar multiple, it's just that same derivative times the scalar multiple. So this would be minus 6. And then the derivative of x is just 1, so we're just going to have the x in the denominator times the natural log of the old base. And there we go. That's all there's to it. So g prime of x equals 1 over x natural log of 2 minus 6x natural log of 5. All right, let's try another one. All right, so we're going to take the derivative of log base 2 of 1 over x. So a is just what's the base? The base is 2. All right, we're taking the log of 1 over x. All right, and that is the same as x to the negative 1. Its derivative is going to be negative x to the negative 2 power, or negative 1 over x squared. All right, so now we're going to use that rule to take the derivative. All right, so I'll just call it dy dx since I don't have f of x in there. So dy dx equals, all right, so we're going to have the derivative of our, so we're going to have, in the numerator, we're going to have we have 1 over x, right? Times natural log of 2. But in the numerator, we're going to have the derivative of that. So that's going to be negative 1 over x squared. There we go. Now, that's a terrible looking complex fraction. Right, so we have the derivative in the numerator, we have what we're taking the log of times natural log of the base in the denominator. So we want to simplify that. All right, so our least common denominator is x squared. So if x squared will multiply, if we multiply by x squared, that will take care of all of the denominators. So we're going to multiply this term by x squared, and this term by x squared. Right? So here, the x squareds would cancel. So we'd have dy dx equals -1 in the numerator. In the denominator, right, so one of the x's will cancel, and we'll have x natural log of 2. And that's going to be our final answer. Okay? So there it is, all nicely simplified out. All right, let's try the next one. All right, so use the laws of logarithms to simplify the expression. So I put the steps over there. We're going to have to use, we're going to use the product and quotient rules first, and that's the product and quotient rules for logs, not necessarily the product and quotient rules for derivatives. As a reminder, the product rule for logs, so the log of a product, is equal to the sum of the logs. And we're going to use the quotient rule. So the quotient the log of a quotient is equal to the difference of the logs. And then we have the power rule for logs. So the power rule for logs is that if we have something raised to a power, that exponent can move in front like a coefficient, right? And that's just the nature of logs, right? So logs changes multiplication to addition, and it changes division into subtraction, and exponential into multiplication. That's its function. All right, now when I originally chose this problem, I wasn't thinking, and this has got y's and x's and y's and z's in it, and you by no means know how to take derivatives with more than one variable in it. So I just changed it. So if it's in your notes, it's now f of x equals log base 5 of 25x to the 7th, and that y is now x plus 1, and then divided by the square root of x plus 1. All right? We can deal with that one. All right, if we were to take the derivative of this, wasn't so bad, right? We just multiplied by x squared. It was okay. Right? But this one here, this one would be terrible. All right? So it'd be much easier to rewrite this, right, and make it simpler. So this is just, we're not taking the derivative yet, we're just rewriting it. So I'm going to break up that product. So we have log base, I have log base 5 of 25x to the 7th, right? And that product is going to become a sum, plus log base 5 x plus 1 minus, I'm trying to squeeze it in here, I'm going to hit my notes are on the side, log base 5, the division, the quotient is now going to become a difference. So square root of x plus 1. All right, so that was our first step. All right, we used the product and quotient rules for logs to separate this out into separate logs. Now we're going to use the power rule to change those exponents to scalar multiples. But first we need to rewrite one of them. So f of x equals log base 5 of 25x to the 7th plus log base 5 x plus 1 minus log base 5 of x plus 1, that's to the 1/2 power. All right, so power rule moves the exponents in front. So this would be f of x equals 7, oh wait, excuse me. We have to split that one up still. Because that exponent is not on the 25, right? It is only on the x to the 7th. So let's split that up. Log base 5 of 25 plus, so this is technically a product, this 25x to the 7th, log base 5 of x to the 7th plus log base 5 of x plus 1 minus log base 5 x plus 1 to the 1/2 power. Now all of that's raised to the 1/2 power. All right, now it's good. Except we can rewrite this one more time. One more time. So what is log base 5 of 25? In other words, what would you have to raise 5 to get 25? Well, that's just 2. So we have f of x equals 2 plus. All right, so now I'm going to move the exponents in front. And then we'll be all ready to take our derivative. And although it seemed like, oh, we had to do a whole lot of steps in the beginning, of x plus log base 5 of x plus 1 minus 1/2 log base 5 of x plus 1. All right, so now we can take the derivative. F prime of x equals derivative of the constant is 0. All right, so now on to the next one. The derivative of 7 times log base 5 of x, all right, so it's just an x, so it's 1 in the numerator, but times 7. So 1 times 7 would make that a 7. And in the denominator, we're going to have just the x, but times log, natural log of 5. And there we go. There's the first one. Plus, right, well, the derivative of x plus 1 is also just 1. So we're just going to have a 1 in the numerator. And we're going to have an x plus 1 times natural log of 5. And then minus, so the derivative of x plus 1 is just 1. So we're going to have a 1 in the numerator. The 2 will be in the denominator for the 1/2. So minus 1 over 2 x plus 1 times natural log of 5. Right, and there we go. That's it. All right, so look how easy the derivative was once we used the properties to rewrite this. Okay. All right, again, this is one we definitely want to use the properties of exponents first. So we're going to use the quotient rule for logs first. That will make this much better. Much better. All right, so this is going to be y equals natural log of x plus 4 minus natural log of x minus 3. All right, so this is natural log, so it doesn't need the natural log of the base. All right, and the derivative of x plus 4 and x minus 3 is just 1. So our derivative, dy dx, is going to be 1 over x plus 4 minus 1 over x minus 3. That's it. Ta-da! All right, not too difficult. But it would have been so much harder if we hadn't split that up. All right, so use those properties of exponents to rewrite these. This one is going to need to be rewritten. All right, so we have tons of stuff there. We're going to use the product and quotient rules first, and then we'll use the power rules like we did before. Y equals, so we've got the log of first of all, we have a log of a product, so and then we have a log of a quotient. So we have y equals the square root of x, natural log square root of x plus natural log x plus 1 squared plus natural log, actually, you know what, let's move this down just a bit. I don't think I need that much room. And this way, I have enough room to keep writing across. Plus the natural log of x plus 2 cubed minus natural log of 4x plus 1. All right, so now we're going to use the power rule. Let's first rewrite that. This is y equals natural log of x to the 1/2 plus natural log of x plus 1 squared plus natural log of x plus 2 cubed minus natural log of 4x plus 1. So now we can use the power rule because now we've got that radical rewritten as an exponent. So y equals 1/2 natural log of x plus 2 natural log of x plus 1 plus 3 natural log of x plus 2 minus natural log of 4x plus 1. All right, now we can take all of our derivatives. Now let's write down, so the derivative of the x is just 1. The derivative of the x plus 1 is just 1. The derivative of the x plus 2 is just 1. But the derivative of 4x plus 1, that's 4. All right, so that one's going to have something in the numerator other than 1. So we have dy dx equals 1/2. Right? So the 1 will be in the numerator, the 2 will be in the denominator, and so will the x. Right? So it's 1 over whatever we're taking the log of times the derivative of that. Well, all these derivatives are 1 except for the last one. And of course, this is natural log, so we don't need any natural log in our denominator. That's just if the base is not e. All right, so we have 1 over 2x plus 2 over x plus 1 plus 3 over x plus 2. Right? And these are just scalar multiples. That's why they're in the numerator. And the last one we have a derivative, we have a chain rule, and so that would be minus 4 over 4x plus 1. Now if there had been a scalar multiple, we would have just multiplied it as well. Right? So there we go. So dy dx equals 1 over 2x, 2 over x plus 1 plus 3 over x plus 2 minus 4 over 4x plus 1. And that's it. All right, so on these logs, simplifying really makes it a lot easier. We want to find, so this one's not log, this one's e to the x. We want to find the equation of the tangent line to the curve y equals e to the x over x plus e to the x at 0, 1. So we must first find the derivative function and then find the value of the derivative at 0, 1. Then we can use point-slope form of an equation to find the desired tangent line equation. But I don't know why we would use point-slope form because we have the y-intercept. So why not just put it in slope-intercept form? Anyhow, let's first of all find the derivative. All right, so y equals e to the x divided by x plus e to the x. All right, so remember this is going to be the product rule. Excuse me, quotient rule. Right, and as a reminder, that would be the derivative of the numerator, so du, times the denominator, so v du minus u, the numerator, times the derivative of the denominator, dv, all over the denominator squared. All right, so u is e to the x, and du is e to the x. V is x plus e to the x, and dv is 1 plus e to the x. There we go, so that's not too bad. All right, so dy dx equals e to the x, the derivative of the numerator, times the denominator, x plus e to the x, and then minus the numerator, which is e to the x, times the derivative of the denominator, which is 1 plus e to the x, all over x plus e to the x squared. Let's pull out a common factor since they both have an e to the x. All right, so dy dx equals e to the x, and then we would have x plus e to the x. Now don't forget to distribute the negative. Minus 1 minus e to the x, all over x plus e to the x squared. All right, so, well, e to the x minus e to the x, that's going to be 0. So now this is dy dx equals e to the x times x minus 1 all over x plus e to the x squared. All right? So now we need to find the, so we're going to plug in 0, x is 0. So let's plug in 0 to find the slope of the tangent line. So slope of the tangent line. That's going to be dy dx, and we're evaluating that at 0, equals e to the 0 times 0 minus 1 all over 0 plus, my shadow's blocking, e to the 0, and that's squared. All right, so e to the 0 is 1. So this is 1 times negative 1. That's negative 1. In the denominator, we have 0 plus 1. So that's 1. 1 squared is 1. So this is negative 1. So that wasn't too difficult. And here's the equation of the tangent line. All right, we have the y-intercept, 0, 1, so it would be y equals negative x plus 1. There we go. So there is our equation of our tangent line. So that wasn't too bad. Even the derivative wasn't too bad. All right, find the equation of the tangent line to the graph. F of x equals 2e to the x plus 6x at x equals 0. This one's even easier. All right, so let's take the derivative. F prime of x equals the derivative of 2e to the x is 2e to the x, and the derivative of 6x is 6. All right, so now we'll plug in 0. So f prime of 0 equals 2 times e to the 0 plus 6. That's going to be 2 plus 6, or 8. All right, so this is the slope of the tangent line. All right, now we need to find the y value of the function. So we need to find f of 0. All right, so that's going to be, that's in the original function. That would be 2e to the 0 plus 6 times 0. All right, so 6 times 0 is 0, and 2e to the 0, that's 2. All right, so our point is 0, 2. Another y-intercept. So now we can just write the equation. So the equation of the tangent line. That would be y equals 8x plus 2. There we go. That's all there is to it. Right? So to find the slope of the tangent line, you substitute whatever x value you're referring to into the derivative. To find the, if you're not given the y value, just plug that back into the original function. Right? And here we have the y-intercept, so why not write it in slope-intercept form? All right, so now let's take a look at this one. So this one's just going to be some reviews. All right, so, and we're going to do all kinds here. All right, so we have a product here because we have x cubed times e to the 2x. And you know what? Actually, let me split this into 2 videos. So I'm going to stop this one, and then I'll record the rest of this on the next video. All right, thanks for watching, and bye for now.